As we conclude our look at universal gravity and Kepler's laws, we're going to do one last example. And the example we're going to look at is distance to satellites. And we're going to use the moon to base our calculations. The particular satellites that we're going to look at is what's called geosynchronous satellites. It's a very special type of satellite that is put in an orbit where it is exactly matched to the Earth's rotation speed. So the Earth rotates at a speed of one revolution or one rotation per day. 24 hours, the sun rises and sets, the Earth is spinning, so it goes. So we get the sun rising and the sun sets. Well, if we wanted to put, say, over the equator, say, pretty much over Hawaii, we wanted to put a satellite that always looks down on Hawaii. What we're going to do is we're going to put a satellite in what's called geosynchronous orbit. So as the Earth does its one rotation or one revolution, this satellite does one revolution or one rotation around the Earth, one revolution around the Earth in the same amount of time. So a geosynchronous orbit is an orbit where a satellite will travel around the Earth in exactly one day. It'll always be overhead. For reasons of it being geosynchronous and having to match the rotation of the Earth, it actually has to be placed over the equator. So it's kind of an interesting spot for it. One thing that I will say on this is that most satellites are not in geosynchronous orbit. Only very few are, and it's really because of the potential energy. And we'll look at that at the very end of this example. So, how are we going to figure out how far to put this thing away from the Earth? That's the big question. We know we need to have an orbital period of 1 day. Well, we know we have another object that orbits the Earth in a specific amount of time, and that's the moon. We know that the moon orbits the Earth in 27 days. So we can use Kepler's third law to figure out how far a geosynchronous satellite, how far do we have to put this guy away, a satellite away from the Earth to make it orbit in 1 day. So we look at Kepler's third laws, and I changed the subscripts just around a little bit, but really it's two quantities. I have a period of the moon and a radius that the moon is away, semi-major axis, a period of the satellite, and the radius that the satellite is away. So I start substituting in numbers. Actually, I start simplifying first. I want to figure out what is the radius that this satellite is away. Well, I look at the period of the satellite, I look at the period of the moon, and the radius of the moon. And I substitute in, combining, pretty straightforward. Take the cube root of everything, so I get this quantity to the 2/3 and the radius of the moon. And I find that the satellite has to be placed for a 1 day period compared to the moon's 27-day period is equal to 1/9 of the distance from the Earth to the moon. So I look in, just solve this number, 2/3 or 1 over 27 raised to the 2/3 is 1/9, which just means that if I look at the distance from the center to where the moon is orbiting and the center to where I have to orbit the satellite, the two distances are a ratio of 1 to 9 to each other. So just very simple application of it, but interesting consequence. As I said before, we normally don't put satellites at that distance. So here are two pictures. They take a little while to get your eyes adjusted for it, but this is kind of a zoomed in picture. We get the Earth, which is drawn to scale, and we actually see where we put different satellites. So we see that most of these satellites are pretty close to the Earth's surface. And International Space Station, which is this purplish color one, shows up around here. Hubble telescope is this green line there. GPS, the system for tracking it, where it finds where your phone is, or if you have a GPS in your car, we put these actually quite a further distance away than the Hubble or the International Space Telescope is, or International Space Station is. And what we're going to do is the geosynchronous orbits are actually quite far out, and the geosynchronous orbit actually defines two different regions. Medium Earth orbit, there's a low Earth orbit, but the medium and the high Earth orbit is separated by this geosynchronous orbit. To get you an idea of what it looks like on a zoomed out scale, here's the Earth again, this is the medium orbit, this is the geosynchronous orbit, and this is the high Earth orbit, this is the Moon is. So from our previous calculations, we hope that from the Earth to the geosynchronous is 1/9 it, and if I put this in, so one distance here, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So the distance, the ratio between the geosynchronous orbit and the Moon's orbit is a ratio of 1 to 9. So it's kind of an interesting thing. Geosynchronous orbits, because they're so far away, they take a lot of fuel to get there. They're very expensive, so we really don't put a lot of stuff there. There's very few satellites in there. There are a lot of satellites close to Earth. This is a lot of the communication ones are up here. We do put some of the communication ones out at the geosynchronous orbits. The GPS system was actually kind of an interesting one, an interesting spot to put it. They figured out that with a small number, they could actually reduce the cost of energy and the expense of it, because GPS would be nice if you put a bunch of them out at the geosynchronous, so you always know that these things are always in the same spot. Well, they put them actually closer in. We put a few more up in it, and the amount of energy we save to do this launch as compared to do this launch is actually cost effective to put more satellites in there. So the reason why we go through all this is GPS puts its satellites at this in-between range where we can use, I think, about 20 satellites to cover our distance, which is a little bit more than we actually would need, but it's cheaper in the long run.